So I want to start by talking about a property called ionization energy. So this first slide, I want you just to participate with me up here. Okay. So find sodium on the periodic table. Okay. How many valence electrons does sodium have?
1.
Okay, sodium has 1 valence electron. Now, what's the magic number of valence electrons the elements want? Okay, they want 8 in that outer shell. So is it easier for sodium to gain 7, or is it easier to lose 1 and drop down to a lower shell number? Okay, so it's going to be easier for sodium to lose 1. So for this next question, I'm just going to put like a -1 there. So it's easier to lose 1 than it is to gain 7. Okay. Now, find fluorine. How many valence electrons does fluorine have?
7.
Okay, fluorine has 7. And what's the magic number of electrons that fluorine wants? 8. Okay, so is it easier for fluorine to gain another electron or to lose 7? Gain 1. Okay, so it's easier for fluorine to gain 1. So now, let's compare sodium to fluorine. Which element do you think it's easier to steal an electron from? Sodium or fluorine? Turn to your neighbor. Tell your neighbor, which one do you think it's easier to steal an electron from, and then why? Okay, who thinks fluorine's the easier one to steal an electron from? Who thinks sodium? Who feels too cool to vote? Okay, sodium is easier to steal an electron from. Why is sodium probably the easier one to take that electron from?
Because it's already trying to get rid of 1.
Okay, it already wants to get rid of 1, right? So it's like, here, have it. Good. So that brings us to our first trend. Okay, so our first trend is called the first ionization energy. You do need to write this definition in your notes, but you can shorten it. Okay, first ionization energy, it's the energy required to remove an electron. Okay, technically it's from the neutral gaseous state of an atom. Okay, however, if that's like too much for you to remember, you just remember it as it's the energy required to remove an electron. Okay, so now look at the trends exploration activity that you filled out on Wednesday, okay? Flip your paper to the one that says ionization energy, okay? So make sure you're looking at the little periodic table that says ionization energy, okay? This is the one that you drew lines. So we're going to look at the trend. We're going to break up the periodic table into columns and rows. So as you go down the column, what's happening to the size of your lines? Are they getting taller or shorter? Good. They're getting, as you go down, they're getting shorter. Okay, so then if you go from bottom to top of the periodic table, what's happening to the lines?
They're getting shorter to taller.
Good. They're going to get bigger. Okay, so ionization energy increases as you move up a column. Okay. And then now take a look at the rows. As you go across the row from left to right, what's happening to the length of your line? Is it getting taller or shorter? Taller. Do you see that on your paper? Your line should be getting taller as you move to the right. So ionization energy also increases as you move from left to right. I would also recommend in your notes, you can draw these 2 arrows like up and over, or you can just draw the diagonal arrow. Okay. So ionization energy, it's going to increase as you move up and to the right of the periodic table. Okay. So what that means is, as you move towards the top right of the periodic table, it's going to be harder to steal an electron. Okay, so it's going to take more energy to steal an electron. So then here's just a picture. These are actual ionization energies. They're measured in a unit called kilojoules per mole. So you can see helium, it takes the most energy. Okay, so helium isn't going to let go of any of its electrons. No way, right? Helium wants its electrons. So if you were going to take it, you need lots and lots of energy. If we look down here at the bottom, we have cesium. Cesium just has a little bit of energy. Is it going to willingly give up an electron? Yeah, take it. It doesn't want it. Take that electron. Okay, in our class, we're only going to talk about first ionization energy. I just want you to be aware that you can have the second ionization energy, which is just now what's the energy required to remove the second electron. Okay, do you think there could be a third ionization energy? Okay, that'd be what's the energy required to move the third electron. Could we keep going? Yeah, we can keep going. In our class, we're only going to look at first ionization energy. Okay, next let's look at atomic size. Okay, on your paper it says atomic radius. Is there a difference between atomic radius and atomic size? No, same thing. Okay, so we're just talking about the size of the atoms. On your paper, it should look something like this. Okay, so if you go down a column, what's happening to the size of circles you drew? Okay. Is yours looking like this? Are they getting bigger? Okay, so as we go down columns of the periodic table, atoms are getting larger. All right, then if we go across the rows, we always look left to right. What's happening to the size of circle? Okay, it's getting smaller. So as you move across the period, they get smaller. Okay, so then it increases going from right to left. Okay. So in your notes, copy down the arrows for the trend, or if you like the diagonal, you can draw the diagonal arrow. Okay, so atoms get larger as you move to the bottom left side of the periodic table. Let's talk about why this trend is what it is. Okay, so going down, this is the easy one to conceptualize. As you go down a column of the periodic table, the shell number increases. Okay. As the shell number increases, the orbital gets bigger. So I think last Friday, did we watch the YouTube video with the orbitals? Do you remember that YouTube video?
Yeah.
Okay, we saw like the little 1s orbital, it was like a small sphere. Then what did the 2s orbital look like?
It was like a little bit
Okay, a little bit bigger. What did the 3s orbital look like?
bigger.
Bigger, okay? So when you go down a column, the shell number gets bigger, the orbital gets bigger, the atom gets bigger. Okay. That one is like easy to understand, yes? Okay, the row one is probably counterintuitive. Okay, so look at the periodic table. We're just gonna look just going across the row. Okay. As you move across the row, the number of protons increases, but also doesn't the number of electrons increase? Okay, so naturally, we would want to think if we're getting more protons, more electrons, more stuff, should the atom get bigger? Right? Yes, you with me there? Give me like a yes, no.
Yes.
Okay, instead, atoms get smaller, which is kind of counterintuitive. The reason they get smaller is you stay in the same shell number. Okay, so like same energy level, same orbital of electrons, except as you go from left to right, every time you move over an element, you get an extra proton in the nucleus. What kind of charge do protons have? Positive. Okay. What kind of charge do electrons have? Okay, they're negative. What do positive and negative charges do?
They make positive.
They attract, okay? So as you move across the period, your nucleus becomes stronger and with a positive charge. Okay, that stronger positive charge is going to pull those electrons in tighter, which makes the atom smaller. Okay, so now let's compare atomic size to ionization energy. Okay. So ionization energy increases as you go up and to the right. Okay. I'm just going to write IE for ionization energy. Atomic radius is the opposite. So it increases to the bottom left. Okay. So I want you to turn to a neighbor in just a minute and talk about why is it that small atoms have really high ionization energies and why do large atoms have really low ionization energies? Okay, so turn to someone next to you and talk about why do you think this is. So small atoms, it's hard to take an electron. Larger atoms, it's easier to take an electron. Okay, why do we think small atoms make it really hard to remove an electron? A real answer? Okay, give me a real answer. No, I'm not ready for that one. Okay, small atoms. What are the subatomic particles that make up an atom? What three things make up an atom?
Electrons, protons.
Okay, protons, neutrons, electrons. What's in the nucleus?
Nucleus.
Okay, protons and neutrons. So what's the charge of the nucleus? Okay, so the nucleus is positive charged. Okay, what are the electrons?
Negative.
Negative charge. If atoms are tiny, how close are the positive charged nucleus to the electrons? They're close. And what do opposite charges do?
Attract.
They attract. Okay. Large atoms, do you still have your positive nucleus and your negative electrons?
Yes, you do.
Okay, it's just now you have more distance between them. So what happens to this attraction? It's weaker. So if this attraction is weaker, is it easier to pull an electron off of it? Yes. Okay. So larger atoms, it's easier to take that electron because they're further. Okay, that attraction is weaker. Okay. Our next trend is something called electronegativity. Let me explain it and then write something down, but you might want to paraphrase. Okay. So electronegativity is an atom's ability to pull electrons towards itself when it's bonding. Okay, so when it's bonding to another atom. A short way to describe it is electron greediness. So let me give you another analogy. We're going to play tug of war. Okay, we're going to think about tug of war.
Oh, I love the word.
You play tug of war with me.
Right now?
I'm just right there,
Okay.
figuratively.
Okay.
I'm going to be hydrogen. Okay? You're going to be fluorine.
Okay.
In order to bond, we got to share the electrons. Okay, so we're sharing, which is like our tug of war rope. We're each going to pull the electrons. Okay. Does someone have to win the game of tug of war? Okay, in this case, fluorine wins the game of tug of war, which means more electrons make it over towards fluorine. Okay. So the more electronegative atom pulls the electrons closer. So it's winning the game of tug of war. Okay. So if you want to write like tug of war, you can write tug of war down. Now that I explained the tug of war, if electron greediness makes sense, can you write electron greediness down? Okay. If you want the full formal definition, can you write that down? You can. I just want to make sure that electronegativity makes sense to you. So it's pulling the electrons towards you in a bond. So if atoms aren't bonding, do they have an electronegativity? Can you play tug of war by yourself? No. 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 Just keep it simple. No. Okay. So it's only for bonded atoms. Okay. As you go down a column, your electronegativity lines, did they get larger or smaller? Smaller, right? As you go down, they should be getting smaller. Okay. So that means electronegativity increases as you go up the columns of the periodic table. And then as you go across the row, as you go from left to right, what's happening to the size of that line? Is it getting larger or smaller? Okay, larger. So electronegativity increases as you move to the right. I would recommend drawing the diagonal on your paper. Okay, so electronegativity increases as you move up into the right side of the periodic table. Okay, do you have the trend for electronegativity?
Yes.
Okay, I want to talk just a little bit about elements. Get down cesium and fluorine. Okay, so get down what I've started. We measure electronegativity with just an arbitrary unit. We call it the Pauling electronegativity scale. Arbitrary means it's made up. Okay, we've made up numbers just to quantify electronegativity. Okay, when we look at electronegativity, noble gases are emitted. Why do you think that is?
Because of the noble gas.
What does it mean if something's a noble gas? Okay, it has 8 valence electrons. If an element already has 8 valence electrons, is it going to bond? Okay, if it's not bonding, is it going to do the game of electron tug of war? No. Okay, so noble gases, they don't bond, so no electronegativity for them. Okay. So then the least electronegative element, we say it's cesium, and it has this value of 0.7. The most electronegative element is fluorine, and it has a value of 4. So that means all the other elements fit into the range between 4 and 7. Okay, so now let's look at the trends for electronegativity and ionization energy put together. Okay, so they both increase up and to the right. Okay, so why is it that the elements that are the hardest to take an electron from are the ones that want to steal electrons from other atoms? Okay. Or why is it that the atoms that want to just give up an electron easily don't want to take electrons from other atoms? Okay. So let's pick on fluorine. Okay, so fluorine's way up here on the periodic table. Okay. Fluorine has how many valence electrons? 7. Okay, 7. And how many does it want to have? 8. So is fluorine really, really, really close to having a filled valence shell? Okay, so fluorine is going to do everything it possibly can to get to 8 valence electrons, which means fluorine is going to take an electron from any other atom. Okay, it's going to steal that electron so it can have a filled ring. If fluorine is trying to steal another element's electron, is it going to give up one of its own? No way. Okay, so fluorine's not going to give up an electron, which is why it has a high ionization energy. Let's look at cesium. Cesium is down here in that first column. So how many valence electrons does cesium have? Okay, 1. Is cesium going to try to gain 7 or lose 1? Okay, cesium is going to try to lose 1. So it basically wants to give away this electron, right? It's going to give it away. If cesium's trying to give away an electron, is it going to want to take electrons from any other atom? No. So it's going to have a low electronegativity. It doesn't want any more electrons. Okay, we're going to do just a couple practice problems. A couple together, then you're going to do some on your own. Okay, a few together, then on your own. What's the element with the highest electronegativity? Just yell it out loud. Okay, so fluorine has the highest electronegativity. What about the lowest electronegativity? Okay, we're going to go cesium. Bottom left. What about the largest radius? What's the biggest atom?
Cesium.
Okay, we're going to go cesium. What about the smallest radius or the smallest atom? Okay, helium. Which one has the highest ionization energy?
Helium.
Okay, also helium, top right. Which one has the lowest ionization energy? Cesium. Okay, so now I'm going to give you 4 elements. We're going to rank them by increasing ionization energy. You're going to do some of these on your own without my help next. So start by just drawing the trend. Okay, so show me with your arm what's the trend for increasing ionization energy. Okay, so draw that on your piece of paper. Okay, put that down. When you do practice problems without me, draw the arrow. So we're going to go increasing, which means smallest to largest. So of these 4 elements, you're going to look at which element is towards the bottom left, like the most towards the bottom and the left, and then you're just going to work your way to which ones are the highest on the right. Okay. So of these 4, which one is the most left and the most low? Okay. RB. So rubidium is all the way on the left and very low on the periodic table. Then which one comes next? Okay, next is potassium. Okay. All right, so that leaves phosphorus and chlorine. Between phosphorus and chlorine, which one's more on the left or bottom?
Phosphorus.
Okay, phosphorus. So then that makes chlorine the most, like the highest ionization energy. Same elements. This time we're going to rank them on increasing electronegativity. Show me with your hand what's the trend for electronegativity. Okay, draw the line on your paper. Okay, is it the same trend? Okay, so which one of those 4 is on the bottom left? Okay, which one goes next? Okay, then which one? Which one goes after potassium? Phosphorus. Okay, is that the same?
Yep.
Is it the same, like, trend? Good. Okay, one more. Last one is atomic radius. So show me with your hand what's the trend for atomic radius.
Atomic radius. Oh, shivering tempers.
Okay, it's the opposite, right? So down and, holy cow, down and to the left.
So it's just
Okay.
everything just on the opposite.
Okay, so of those 4 elements, which one's closest to the top right now? Okay, so then it's chlorine, then what?
Phosphorus,
Phosphorus, then,
potassium,
and
rubidium.